Continuing on from part 3, now I'm proceeding to design a custom PCB daughter board as a replacement for the Atari Sally custom CPU. In the previous part we've seen that the breadboard prototype for this circuit seemed to work just fine except for what seemed to be some parasitic effects related to the long wires and the suboptimal connections of the breadboard. But I felt confident enough to proceed and design a prototype custom PCB. I'm trying to reduce as much as possible the effects that could compromise the signal integrity in this board. So I'm doing a ground plane, as you saw there in blue, and I'm doing some copper flooding also related to the ground plane on the two inner layers of this 4-layer PCB as well. This shouldn't make any difference in a low-frequency circuit like this Atari. This is more important when you're dealing with hundreds of megahertz or gigahertz. Here probably doesn't have any effect, but in the worst-case scenario, no, it works as a heat sink for this board. Also makes more electrons available locally because real physical electricity flows from ground to positive. Only conventional electricity flows from positive to ground. So this should help there a little bit as well. Now this is how the top layer of the board will look like once it's manufactured. And then this is a little 3D model to make sure that all the pins are visible, that I can install everything correctly. And here's the little PCB back from the manufacturers. It looks great. Because it's a little bit translucent, you can even see the copper flooding in the inner layers, in the in-between layers. I will come to regret having done this, as you will see later in this episode. Copper flooding is harmless enough when you're designing a motherboard. It helps create some extra capacitance locally, so it smoothens the signal, helps with bypass. But this is a daughter board whose ground is connected to the motherboard via one single small pin. And that can lead to problems related to the copper flooding I did. But stay with me. Let's see how this will evolve. Now I'm checking to see if the pin headers that I selected to use with this little daughter board will have enough height to prevent the daughter board from competing for space with any of the surrounding circuitry. As you see, it will fit just fine. I just put the pin headers in the socket. I'm going to fit the little daughter card on top of them now. There you go. And it seems to fit just fine. There is enough room all around. It is not conflicting with anything around space-wise. So we are good to go to install these pin headers and populate our little board with its components. So let's go ahead and do a time lapse so you see what has gone on. Here I'm just checking with the multimeter to make sure I didn't cause any short circuit between adjacent pins while soldering it. And now I'm installing the chips directly without sockets in order to not consume too much vertical space because the keyboard will come on top of it. And if you wonder why I'm alternating sides as I'm soldering, it's to prevent one part of the chip from becoming overheated. If I follow just the sequence in order, that could be a danger. Okay, here's our little board, fully populated. Show you here as well. I have changed the socket on the main board. It is now a gold-plated precision socket because I want to optimize as much as possible the connection from the motherboard to this little daughter board to avoid parasitics, to avoid power supply problems, to optimize it as much as possible. So there we have the new socket. This is the original Sally chip that has been removed. Let's populate the board now with our little adapter. There it is. I'm already all set with the oscilloscope to measure the signal so we can compare with the previous tests we did on the breadboard to see how the signal quality changes. The TV is all set. Let me film this for you. Okay, there's our little adapter. I'm all set with the oscilloscope. TV is ready, so let's just, this is on, let's turn it on here, and let's see what happens. Oh, this is not looking good. This is actually similar to what we had on the breadboard, but worse. It doesn't get to the ready and the prompt like we did get with the breadboard, so somehow this is worse than the prototype on the breadboard. Maybe I did something wrong when I populated it. Let me have a look. Well, actually I didn't. I have now probed every single connection. I sounded it out with the multimeter in continuity mode, and the board is perfectly all right. It is exactly what I designed. The design intent has been captured here. First thing we should look is at the power signal, so we see if the parasitics have improved. Yeah, this is a lot better. There's a lot less oscillation on the signal. Clearly, there's less parasitics on this little daughter board. The bypass capacitors are doing their job. Let's have a look at the input clock to the system, which is here on this pin. It's a pretty well-shaped clock, even though it's only going to 4 volts. But if we look at what comes out from our attempt to boost the clock with these bus transceivers, we should get a 1098. We get this. Yeah, so this is this goes to 5 volts almost. 5 volts is this line here. There is some oscillation that you see here on both levels. Yeah, the bypass capacitors are not ideal, but this shouldn't be a problem. The levels are good, the transition is fast, so these oscillations shouldn't be a problem. Yeah, let's look at the input halt signal, which should be this. Yeah, that's the halt signal coming in. If we just stop it, we see that sometimes it's active low, exactly as it's supposed to be. Yeah, this looks okay. What we have to do now is compare what's happening here, the signals that we see here, with the equivalent signals when I use the original Atari Sally. So let me get a reference now with the Atari Sally, and then we can compare it. Pull this one out gently. Put the Sally back in here. And with the Sally, as you see there, here on the TV, it does work. I'm particularly interested in two signals, as we've reviewed previous time. Two signals are changed here. The read-write signal is processed by being ORed with the inverted latched version of the halt signal, and the latched version of the halt signal controls whether the clock passes through to the CPU or not. So these are the two critical points. Let me probe with the oscilloscope where they are. Let me start with the read-write signal that the Sally puts out to the other parts of the system. There we have it. So when it's low, it's a write. The rest of the time, it's a read. So you see the CPU is more often reading than writing. And the oscilloscope manages to get synchronization largely, except occasionally you have a blink somewhere else. This is not a regular periodic wave, so it's difficult to talk about frequency. But when the oscilloscope tries to interpolate, it goes between 40 kilohertz and 42 kilohertz. So the writes are happening on average with a frequency of about 41, 42 kilohertz for the read-write signal. So let's compare the read-write signal that the adapter is putting out on this pin. So the shape of the signal is the same. I hope you can see it here. But when the oscilloscope tries to interpolate the frequency, it finds, instead of 41, 42, it is finding 50 to 54 kilohertz. Now, this could mean that there is a problem on how we generated the logic for the read-write signal, that it is not exactly as it was in the original Atari architecture, the 400 and 800. They did it differently in the Sally. And again, I don't have access to the Sally, so I'm trying to reverse engineer something that I can't see. But this is a clear difference. It is a 20% difference in the frequency with which the writes happen. It could be simply that this computer, because it's not working with the adapter, it's stopping at a different state than the one that works fully with the Sally chip. And it's this difference in the state where it stops that we see here, and not necessarily a problem in the read-write logic. I don't know, but this is a clue. And then why did the breadboard prototype work better? It went further than what you see here. Maybe because the parasitics were such that sporadically they actually got the system to advance a little more by pure chance. That could very well be, because right now it's pretty stable and it's not showing the ready prompt. So it could be that the parasitics actually worked in our favor by pure chance, by sporadically getting the timing right. Let's look at the address bus. The shape is okay, but the signal level, just like before, well, it's a little higher. Before it was 3 volts, now it's close to 3.5. But the level is still low. So the low level on the address bus was not corruption because of the parasitics. It is the main board, the motherboard, because of some fan-out issue, whatever, that is pulling the high level actually lower than it should be. I wonder if with the original Sally we would see this as well. Let's check that. So, pull this out again. Put the Sally back in. There it is. Turn it on. Starting up correctly, as you see there on the TV. Let's see this address pin here. Yeah, it's exactly the same thing. It's exactly the same thing. Yeah, so this low level on the address bus is actually okay. The computer does recognize this as a high, as a 1, even though the voltage level is so low. And indeed, it is the board that is loading the address bus and bringing these levels down, but it's doing that in such a way that it doesn't compromise the proper working of the computer, the proper functioning of the computer. It is still working correctly. Okay, I've now put the breadboard circuit back together. I had removed a few components, but I sounded every connection out with the multimeter, and it's correct in the sense that it is according to the design intent. In fact, I had already sounded out our little adapter as well. It's supposed to be the same thing, and it is the exact same circuit in it as the one that is in here now. I did check every single connection with the multimeter. So I'm ready to test it. Let me turn on the power supply. Let's see. Huh. Yeah. I mean, of course, you have detritus on the screen. There is some corruption of the video memory. When the computer boots, you get a ready prompt, you get the cursor. This is really peculiar. Okay, this is the schematics of my little adapter. We know two things now, we've observed two things. One is related to this board read-write bit in here, which is the signal produced by the SALI chip or my adapter to inform the rest of the system whether the CPU is trying to read from the bus or write to the data bus. This is data bus related. We've seen that in the SALI CPU, the frequency of writes or write values for this signal is up to 20% different than my adapter. So something related to this signal is wrong. We also know that whatever the problem is, it is very timing sensitive. And I say that because the parasitics in the breadboard, which screw up all the timings, the rising time, the fall time of the different signals, serendipitously seems to alleviate the problem. So whatever the problem is, it's very sensitive to timing. Now, there is one thing on this board here, on this schematics, that could explain both observations, and it's the use of the read-write bit to control the data bus transceiver I am using in the adapter. Notice that this net here, read-write bit, comes straight from the modern 6502 CPU that I have added to the adapter. And it is not masked by a version of a latched version of the halt signal as the BRWB control bit is. This is the unmasked version. This is the masked version. And the difference you can see here, this RWB comes from the processor and goes into the NOR chip. And out of it, after masking through the halt signal, which eventually comes from here, well, actually all the way from there, then it's boosted and it goes into in here, it's processed, and then it goes into this NOR chip. This signal is the masked version of RWB with the latched version of the halt signal. So this and this are different, and what can happen is that in a fraction of a clock cycle, the CPU may be going into a high impedance state because of the halt signal, and then the data bus goes into a high impedance state here. But this bit, control bit here, is still in the write mode. So although the transceiver will be seeing nothing on its inputs, it will still be enabled because I've grounded the output enable bit, which is active low. It will be enabled and we'll have a directional bit here on write mode. So it will be putting out a spurious signal on the data bus while the antique is trying to read or write to or from the data bus. And this is probably the source of the problem. I did think about it when I designed these schematics, but I figured, well, it doesn't make a difference anyway, because, this will be in high impedance, and then there will be nothing on the output. But yeah, electrically, this can still generate an interference for a fraction of a clock cycle now and then in a very timing dependent way. So the solution is pretty simple. We just put in here the board read-write bit, the masked version of the read-write bit, such that the adapter internally will work on the same basis as the rest of the system. There will be no conflict with the rest of the system, a situation in which the rest of the system thinks the CPU is on read mode or halted, but this transceiver is actually putting a spurious signal on the data bus because the directional bit is on write mode. This should explain it. Let's see whether this simple solution works. Okay, so the read-write bit is on this transceiver. It's this wire here, the red one here. So instead of having this come from the CPU, I will have it come here from pin 1 of the flip-flop chips, which is the same signal that goes to the rest of the board. I'll need a longer wire for that. And it goes to pin 1 of the NOR. Yeah. Okay, modification is done. Let's see. Ha! That seems to be it. That seems to be it. One bloody wrong connection. And the parasitics are still there. Let's look at the power signal. Yeah, it's a mess. It can dip down to 3 volts. But it's not really causing that much trouble. Yeah, this is a TTL circuit. It's not that sensitive as today's advanced CMOS circuits. Let's test it with the cartridge now. I'll even connect a joystick. It allows us to test a little more. Okay, so the cartridge is on. There is no Sally CPU, it's just the stuff on the breadboard, parasitics and all. Let's see how far it goes with the cartridge. It just works! We can play Battlezone without a Sally chip. Oh man, how stupid I have been. Unbelievable. And on that cheerful note, I decided to hack into the little adapter to lift one of the pins of one of the transceivers, the direction pin, and pass a bodge so it gets the right signal, the same board read-write bit that is exported out of the adapter to the rest of the board. And now the hope is that the little PCB will work just as well as the breadboard does. There it is, with the little bodge from pin 1 of transceiver 2 all the way to pin 35 of the pin header. That will make sure that both the transceiver and the rest of the board get the same read-write bit. Power is going to be on now. That's the big moment. 3, 2, 1. Now, how is it possible that the breadboard works perfectly and this doesn't. Yeah, that's certainly puzzling and bad news, but if you pay attention, you will notice that although we don't get the ready prompt, the computer hasn't booted properly, the screen is a lot cleaner. There is a lot less rubbish in the video memory, so we did solve something important. The problem is we haven't solved it all yet. The plot thickens. Well, pretty obviously, there is a problem with the PCB, not with the circuit, because it works perfectly well now. As you can see, even the screensaver of the Atari 800 XL is working. Now, it's very difficult, once you have the correct schematics, to make a mistake on the PCB itself, because the tool, the EDA tool, makes sure that you don't make connections here that aren't there, or that you miss some connection. So yeah, could it be a component that is at fault? So what I'm going to do now is I'm going to take another board, the same design, just another board. I purchased 10 of them. But before I populate another one, there is one more thing I want to try on the breadboard, of course, and that has to do with the bus enable signal that I want to use to enable or disable the data bus transceiver, this guy in here. Right now, if you look at the schematics and the data sheet, right now, let me see, the output enable is pin 19, which is this one here. Right now it's grounded, and output enable is active low. So right now, this transceiver, which is this, is always enabled. Even when the data bus of the processor itself is disabled and goes into a high impedance state, this one here remains enabled because of this wire here, which is grounding it. So I'm going to remove this wire, and I'm going to use as transceiver enable signal. In other words, I just removed this ground here from pin 19, and I'm going to use the same signal, bus enable, that goes to pin 36 of the processor. I'm going to use the same one on pin 19. It shouldn't change anything because it's working as it was. It's just an attempt to make it cleaner, so when I populate another board, if this works as well, then I will lift another pin, this one here, and make all the connections as strictly as they should be, just to be safe. Let me get the jumper. Pin 36, 40, 39, 38, 37, 36 goes into pin 19 of the data bus transceiver. Let's see if it still works. If it still works, I'm going to modify the design according to these two changes we've just made and populate another board accordingly. Everything is done. Yeah, let's turn it on, see if it works. Aha, it doesn't. It doesn't. Because the bus enable is active high. So it will never enable the data bus. So I cannot, I have to take the inverted version of this. Do I have it? I do. The problem is that this one is active low and bus enable is active high. So we have to take the opposite of bus enable, which is this one here, bar 1Q. So we just have to add a little net from here all the way there over here. And that's pretty much it. Now this transceiver will be disabled together with the data and address buses of the CPU. And whenever the data and address buses of the CPU will be enabled, so will the transceiver. So this should eliminate a little bit of crosstalk, a little bit of interference in the data bus. As we saw, the system does work the way it was before by keeping this enabled all the time, but now I am in the mood of keeping everything as tidy as possible to avoid more surprises in the next interaction of this board. So in 19 and 6 here. Yeah. Let's try it again. Yeah, it puts fine. Let's try the cartridge and play a game to make absolutely sure. Battle's on again because I don't need the start button to start the game. Yeah, it works fine. And with that, I went on to populate another copy of the board with brand new chips and the two modifications we just discussed, two little bodge wires that you can see in there going to the same transceiver. And the question is, will it then finally work, or will we face more problems still? Stay tuned for the conclusion of this episode in the upcoming part 5.